Our power session. My name is Yang. I'm a faculty member in the power domain. So, in power domain, we have two subgroups of faculty members on the transmission and distribution. There's also another classification of the faculty members where it's more of a traditional analysis, like stability analysis, and the other side is more data-driven, that is artificial intelligence. So that will be the four categories that I'm going to introduce to you today. So in the middle, if you have any questions, stop me. We have enough time. I want to clarify as much as possible so that you can pursue what you are going to do in the next 1 or 2 years. We have enough faculty members, and we are very happy for you to join each group of our subdivision. So for power system, typically when I try to sell my story in proposals to Department of Energy or National Science Foundation, I say, we are doing the biggest machine in the world. What is a machine? Machine is basically the connectivities over different components, while mechanical structure or other means. But power system, as long as you have a cable, you can connect everybody together. So that is why the machine is massive and need a lot of attention. So in 2003, there's a blackout in New York. What's happening? That machine is sick. So then you need a lot of engineers like me to fix the problem. So in our domain, we have a lot of diversity. What do I mean by diversity? For example, if you are going to follow the communication division, they are information theory. They are control theory. For us, we are power system. So it's not a theory. It's more like a system. When we have different components, how we combine them together. So that's why in our program, you can learn many different protocols and many different engineering perspectives. So another thing I want to highlight is, I was at Stanford University and I joined here 4 years ago. So why did I join over here? I did get a lot of interviews, but ASU is ranking, at least to my perspective, ranking top 3 in power engineering. Because there was a time 25 years ago when people are leaving power engineering, ASU keep the tradition. So there are many famous professors in our group who was getting through that hard time. So that's why our program has the most comprehensive knowledge for you to learn. Okay? So that's why they say, we are the top 3 programs. And also within the 14 faculty members, we have 3 National Academy of Engineering members. That's a very high ratio, even when you are talking to MIT and Stanford faculty members. And our graduate also has a very nice job opportunities. For example, last semester, 5 of my students asked me, hey, Yang, can you get us internship? I just shoot 5 emails. They don't apply, they get the job immediately. So that is the relationship and close relationship we had with our industrial partners. For example, one was going to the National Renewable Laboratory in Denver. The other is going to PNL. The third one went to APRI. APRI is the Energy Electrical Research institution, something like that. So it's relatively easy. But I do want to tell you one shortcoming of our domain. Our salary is not the top. If you compare the salary of a power engineer to a salary of a computer scientist, no, we are not that high. But we are very stable. Once you get the job, you get the job for your lifetime. So that's the last selling point over here. So those are the faculty members. So this is a NAE number, National Academy of Engineering. This is another one, who is helping people to understand what the California blackout was, like looking into the generator when it's tripping, what's happening. And then, this is another NAE member, Vijay Vitar. He was doing stability analysis. So if you join our program, you have opportunities to talk to them 3. You can try to talk to them. They are relatively friendly and the group is large. Okay, but you can see we have 14 members. You can try. So in our domain, you need to take some classes to understand it better. So this is like a chronicle relationship when we start from the beginning. So energy system and power electronics, for example, I'm going to teach that one. So that is an undergrad level class. It's very popular. A lot of students take that class. You need to have labs. And we have a lot of donations from our partner. That's another uniqueness of power group in ASU. We have all the equipment ready. Then you can go further in the graduate level. With special permission, undergrad can also go there. Nuclear power engineering. Right now, it's not popular. However, my advisor at MIT told me, she actually believes a lot in nuclear power. But anyway, if you have an interest, we have the biggest nuclear power station, probably to the east of ASU. We typically organize tours over there once every 2 years. So you can have a look of what the most secure nuclear power station look like. And then we have electrical power plants. For example, in the past, I say I need power. You see on the University Avenue, when you go to the east, there's a bizarre area where you see some towers. So that's a gas generator. That gas generator is trying to ramp up when people increase their load immediately. For example, you are using your EV to have level 3 charging, fast charging Tesla car. So then you need to actually look into how the power plants, different types of power plants are coordinating with each other. Hydro power plant. Stable, but cannot ramp up very fast. Gas generator, they are running all the time, but I don't pick up them at the same time. I say, okay, you guys just run. Okay, when I need one more, I just connect one more. But everybody's standing by. This is like a game. But there's a lot of things that we can zoom in all the way to the PV generation. How that is going to be a new resource. And then you can go to the power devices. System. System means you have many components. Each component has its own usage, input and output relationship if you put it in a signal processing way. So in this class, you will learn how different devices are working, like inverter. You generate your DC power at home, 5 volts, always too low. Then you want to convert it into AC, so SRP will buy your energy. Right? Then you need a device to magically change it from a flat signal into sinusoidal waveform. So that is what you are going to learn about this class. And then power system analysis. You know how the power are generated from one place, another place. And then how it is consumed by many devices in your grid. Then it's time for you to have a big picture. You say, hey, I want to work in Washington, D.C. I want to design the next generation standards for our nation. Then you need to understand what is the weakest point. Is Chicago the weakest point? Or Los Angeles is the weakest point? And then what you need to do next. That's how power system analysis is going to do the job for you. For example, you will use linear algebra, eigenvalue analysis. You will even look into differential equations that you guys learned in the past to see how you can magically connect the eigenvalue to a cascading failure and then report maybe to the president, hey, there's a weak point. Let's invest $10 billion over there. So that's another thing you will learn over here, and this is the core class of our domain. You can go further, power electronics. So this is really zooming into the technology. So there are 3 faculty members who are building the devices. Like me, I talk. I do data analysis, but I don't create hardware. There are 3 faculty members who are creating the chips. If you have an interest to do the circuit analysis and build hardware by yourself, this class is a very important one. And the salary over here is relatively higher than the salary over power system, in my opinion. 473, electrical machinery. Over here, you can learn what do we define as a machine. For example, in computer science, they have their machine learning. They have their Boltzmann machine. In our domain, we also have our machine. Generator is a machine. So in this class, you will learn many definitions in our domain, how machine is represented in the sense of small components like power electronic devices. And finally, you have the senior design project. So for example, right now, I'm in charge of a senior design project with 4 undergrad. So what they are doing is they are using robots, the small robots. They bought it from Amazon, $100 per device. And then we try to have a urban area, Tempe. So we download the Google map and print it in a very large floor plan. And then they are trying to convert the traffic information from Google map onto this physical map. And those robots, 5 of them, are trying to locate the EV charging station. And then what we do is we use the coils like your cell phone. Your cell phone can have wireless charging, if you are rich. My cell phone cannot do that. But we let the EV have wireless charging of the generators surrounding that grid. So that is the interesting part of the senior design. Now, concentrations and electrical systems. So 360, as I emphasized, I'm going to teach this class next semester. It's going to be a core class. It will cover all the basics in our domain. Yeah, but at a rough level. And then you need to have at least 9 hours of our electives in the power domain in order to get our recognition of your degree. Yeah, you can get EEE 460 something, 470. For example, in this master, I'm teaching 479, transmission distribution. Here, I'm going to introduce you what is a transformer, what is a nuclear power station, what is a protective device, what is a safe overhand for human beings. So a lot of information to keep in mind as a basics. So those are what you are needed. And finally, you need a capstone senior design with us. Yeah, so those are the 3 requirements. 1 class over here, 3 classes over here with multiple choices, and finally a design. Okay. So when you choose the classes, you may ask, oh, professor, you have a very nice advertisement, but I don't know which class I should choose. Then what you need to understand is you need to have a big picture. One is the generation. The second is transmission and distribution. The third one is electricity utilization. For example, in Los Angeles and San Francisco, in the winter, they do not have a lot of generations. So they try to import power from Seattle area and all the way go to Canada. There is a lot of hydro energy over there. So that means you need to understand where the generation is. However, the generation is there. You need to transmit the power to San Francisco, so many people there. Then what are you going to focus on? Good news and bad news, right? How much revenue the utility is going to get and how much power is going to be lost. So that means the second portion of you is you keep on thinking, oh, a lot of power, a lot of money, but I don't want to lose anything. I don't want any destabilized situation to happen. Then you need to do elegant design or smart design over here. And finally, you come to the utility level like SRP and APS over here. So what should I do? I should first keep my customer happy. Yeah, happiness is actually number 1 criteria for them. Number 2, they were thinking about how to gain revenue. That's why they design different programs. For example, you say, oh, I'm a Tesla owner. I want to charge my car. Then they say, hey, come here, it's cheaper. Come there, it's more expensive. But when you come to here, I have an easy setup. Yeah, the transformer is not going to be overloaded. That's why I give you a cheaper price. But you need to understand how to design this utilization scheme in the best way. Yeah, finally, you can go all the way to your home level. Yeah, for example, right now, I think, last week I was at SRP. They were trying to think how to encourage people to sell power to their grid. Because right now, they don't encourage you to do that. They feel, oh, you are another generator. I hate too many generators. So they are trying to ask you to use a storage device to store the power that you receive from the sun in the daytime, and then maybe use it later. However, when I was at Stanford, many of my colleagues from Stanford National Lab, they try to sell the power back. That means PG&E is better than SRP in that sense about the program design. But anyway, if you join our program, you can also try to join utilities to have a better mechanism for people to participate in this final sector of power system. But to summarize, if you want to choose 3 classes that is the best for your future, I will make the suggestion. 1 class over here, 1 class over here, and another class to the end. This will give you a nice picture with 3 classes in the middle. Okay? Yeah, these are some highlights, what they are doing. All right. Then you may say, power system is kind of old, right? It's a machine, but the machine is there forever. And can I do anything to the power grid? No. The cables are there for a long time. Then I want to tell you, you actually can go beyond the traditional concept of power system engineering. This is when we go to the airplane and the ships. For example, 3 years ago, I remember, at that time we were competing for Department of Energy fundings. University of Central Florida get a whole bunch of $20 million for all electricity submarine. So it's a lot of money, but on the other side, you can see over there, the power program is dedicated to build a microgrid inside your ship. If you go to the air, you also need to build all the electricity supporting systems so that people can feel comfortable, all the services can come together. Then you have your mini generator. your mini transmission or distribution, and your mini management over the TV in front of your seat or other parts. So you definitely can go beyond. And they need electrical engineering students like you. Another thing is about the future. You know, we have so many generations. In Arizona, we are trying to sell power to California, but they don't buy our energy because our energy is too cheap. Then their solar panel may not survive. But anyway, we do have two big solar plants when you are driving on the highway from Phoenix all the way to California. So then the question is, if somebody wants to buy my energy, how do I design these solar panels? If somebody do not want to buy my energy, I want to send it to somewhere else, how I can, one, still make the generator work, and two, how to keep it at the optimal operating position. So last year, I partnered with Virginia Tech with a proposal. So there, my job is I try to learn the historical data of the solar panel. Then I say, oh, sometimes people don't want that much power of you. Then I try to do adjustment among different solar panels. Then my job is to keep the solar panel live as long as possible. So that's one example. You can do data analytics even for solar panel analysis over here. I went to Denmark 4 years ago. There are so many wind turbines. They claim they have 95% of the generation coming from the solar turbine because there's an ocean surrounding that area. Then I asked them, I say, you lose your inertia. You know, when there's wind, you have power. When the wind is gone, you guys have a blackout. They say, you know what? In rich countries, we try to get a lot of renewables to have a nice concept. But all the nuclear power station and the traditional power station are actually getting into the Eastern European region. Why? Because they are interconnected. It's only a reorganization of the power, new generation in the northwest region, and old one are moving to the southeast. So that's something interesting for you to learn. We cannot only have the new type of power generation. It's very expensive. Okay, and then you see solar wind turbine, and solar again, and then how are you going to do the analysis? So this is really zooming into your power electronic design. For example, over here you can see some. Anybody know what's this? What is this device? It's from circuit.
Transistor.
Transistor. Okay. All right. Yeah, you can see. You have one transistor, it can do some job. But if I magically combine them into 12 of them, it can be into a power electronic device. That's also how we are going to teach you guys how to go from the basics to more complicated design to make it work. Power generation. 463, 460. So over here you can see so many different kinds of generation mechanism. On the roof of ERC, we also have the biomass generator. So you can go up and have a look. There we also have solar panel. 460, nuclear power engineering. You can learn how to protect yourself if there's a nuclear disaster. On the other hand, you can also learn how people maintain the whole nuclear power station in a safe way. Okay. Finally, I will come back to my beginning of this talk. I say this topic or this area is mostly about a system. That's why it's power system. It's not about theory. However, if you want to dig in, you can definitely have many communication theory, control theory inside our domain. Okay, now let's go to the second one, transmission and distribution. 470, electrical power devices. So over there, that's how you are going to connect to your basics, like differential equations, your algebraic equations. And then we will also talk about devices, like insulation, coordination. What is an insulation? What is an insulator?
Cannot transmit electricity.
Okay, good. Why I should let power to go, right? Why I will prevent power to go by having a insulator? What's the usage of insulator?
Because it can cause damage.
Can cause damage?
Yeah.
Okay. Damage to what?
To people, to stuff.
Nice. Good job. There are cables over here. We typically try to put some rubber cover over there. So that's an insulator. what's that doing? It's trying to not energize the professor. Otherwise, I will go to the hospital immediately, right? So that is one naive example of an insulator. But we have more insulators. For example, if you see big towers on the road, typically they are like this, right? A big tower and some cables come through and there are something holding them. And when you are looking into that devices, you see many plates, one after the other. What are those? They are insulators. Yeah, so there are many devices you can do investigation, and then you are coupling into the material science. What material will have the best insulation capability? 471, power system analysis. Yeah, this is taught by a faculty member, Mojidash. Yeah, she will teach you how you can do power system level analysis. For example, you have the cables. What is the conductor value? What is the impedance value? Okay, once you know those values, how are you going to understand the power flow in the system? For example, currently I have a project with SRP. They have a trouble. What is the trouble? They have a generator in the north region of Arizona, and that generator is trying to support Phoenix. But they have two routes. One is going from north to the south. The other is going a little bit to the east and then go to the south. What they find is in the summer, it's typically unbalanced. Like one line is overloaded, get hot, and very easy to maybe have a blackout. The other one is very lightly loaded. Then they ask us, oh my God, what I should do is I should build another line that is very close to the congested line. But we don't want to do that. It's very expensive. You know, we need to talk to Native Americans to negotiate on the lands, build more towers, cables. You know, 5 years we estimate that will be the time when we have that cable. Our analysis is we try to increase the impedance on that congested line. If you learn circuit, if you have two parallel line, right? So to reduce the current going on one line, I can increase the impedance. So more current is going to the other route. So we are doing exactly what that is going to do. So this is about power system analysis. You try to understand what are the key factors for the power circulation in the system, and then you try to do some magic to change some devices to make it as easy as possible for people to operate. In this one, you will also go to the device level. For example, this is a data center. I talked to Amazon people last year in a general meeting. I asked them, hey, can you give me some project, some money for me to work? They say, what can you do? I say, I can do demand response. They say, what is demand response? I say, for example, your center is at Ohio. Your center actually occupy or consume 2% of power that are generated in Ohio. I say, I can reduce that cost by 10% for you by doing demand response, like pre-cooling of the data center, let some machine to run a little bit earlier. But in the end, they say, oh yeah, we don't want to do that. They say, we don't care about the money. What we care is the data center will always maximize its production. But what I want to tell you is, this is definitely a big monster in our power domain. It consumes 1% power of all United States. And then you will also see some very elegant machines. We actually have many of these devices in our lab. You can have a look. So smart, efficient appliances. You will have the converter. If you remember, you talk about transistors, right? That is only one part over here. And then when you build multiple of them, then you have this machine. Sometimes we hate our vendor because they make it very expensive. But anyway, that's how we can have a higher salary. Tesla car, EV charger. We typically put the battery in the floor level. Then you can design how to maximize that efficiency by yourself. For example, 1 month ago, Tesla sent an email to our group, say, do you have any student for internship? So that's another thing. If you want to go to Tesla, you can join transportation program. You can join electrical power engineering program like us. You can also join some other like data analytics program. So that's our coverage. The third one is now we need to utilize the power. 472 and 473 are the courses that is for your best interest. Anyway, over here, you need to understand how the electronic devices is going to consume your power. So when I was doing my computer science degree in Carnegie Mellon University, there was a postdoc coming from MIT, and then he joined CMU. What he was doing is load disaggregation. what's the story? He said, I just look into your smart meter. And then I can understand what you are doing all the time, who you are dating, what machine you are using, at what time. So he actually can understand your user behavior. But how did you do that? You actually need to have some supervision from the predefined pattern. For example, if you have a refrigerator, how many levels does it go? For example, when you are at home, you hear noises from refrigerator, right? Sometimes it's on, sometimes it's off. Actually, there's a cycle there for air conditioner. Right? Oh, when it's very hot, I want to make it decrease the temperature immediately. There is also different patterns. So that patterns are actually the information you can use to make it most convenient for you. So that is why in this power electronic part, you can do a lot. Finally, electrical machine. Operating principles. For example, there are programs like energy efficiency. So in California, they try to give you an incentive if your machine is very energy inefficient. It's about $50 to $100 if you replace some of the machine at your home. How people are doing that? They are doing an investigation on their understanding of whether your home is at a high efficiency or low efficiency. If your home is at low efficiency, they will go to your home and have a look and then give you a rebate to see whether you want to do that change or not. Okay, design. I talked to you about the design. This is my design this semester. It's for wireless charging for electrical vehicles, how they coordinate for the best price. The other designs, differential protection. Let's say a Tesla car, 10 Tesla car charging simultaneously. The cable cannot support them, then it gets burned. Then you need a lot of protection before that is happening. Maybe when there are 2 cars, you need to send a warning. When there are 3 cars, you need to trip the line by yourself before something like a disaster that is going to happen. Okay, generation strategy, like a policymaker in Washington, D.C. Energy sculpture, drinking fountain. Oh, I don't know what this is, but by the name you can see it's very interesting. Anyway, I am not knowledgeable for everything on these slides. Solar, okay, solar related, and we have an expert who is going to introduce more. And solar energy again, as you can see, solar is really very important in the near future. Okay, right. So what we want to do, in the end of the day, let's say you spend 20 years in power engineering domain. What are you doing? You earn some salaries, but you are trying to change the paradigm or change what we are operating in the past half a century into a new operational scheme. So in the past, we don't have much renewables, but in the future, maybe we want 75% of the renewables. If not, 50%, something. However, there are many technology barriers that you are facing when you are moving. So then this is what you are doing. You do analysis, you do simulation, you try to understand the theory, you propose more theorems for people to follow. So innovation are coming when you are comparing the future and the past. For example, I got 7 best paper awards in the past 7 years. So I want to tell you, if you invest a lot of time in the analysis, it's very easy to make innovation in our domain. Smart grid, EV, solar. Actually, they say everything in your home can be embedded with an Intel chip, and then they can talk to each other. All right. So after you finish the program, you get the degree. What else do you get? You can partner with many research centers. One research center is over here, PCERC. So I get 1 project from PCERC. So it includes 40 industrial members. That means you can get a lot of connections to the industrial in the near future. For example, they send advertisement to our student. Say, hey, ASU student, Georgia Tech student, only 13 universities will receive their advertisement, but only in our power group at ASU. So this one, ASU is actually the headquarters. The universities include University of Wisconsin-Madison, UIUC, Georgia Tech. So 13 of them. Another one is Power America. Over here you can see you can do wide bandgap semiconductor analysis. This is our power lab. So in this power lab we have a lot of space for you to do hardware design. And there's also a supercomputer in this room. It is called Hardware in the Loop Simulator. It's OpenRT. So a lot of things you can do, and there are also motor drive lab over here. Oh, this is my lab. I didn't know they put my picture over there. Yeah. So over here, yeah, you can see this is a protection device. You can see it's nasty, yeah, but you know, it's in design phase. So we try to change the cable here and there and see what's happening. Over here, there are some devices. So what we do is we use a cable to short circuit some part of the place, and then it gets burned, you know, yeah. But we are happy because we want to test whether the protection device will do that or not. So in the past, they trigger one alarm to the university level, burned. But you know, that's what we do, right? We try to see the disaster beforehand than the other folks. These are other equipment that we have. Synchronous machine. This is a gas generator. And then we have many small boxes for you to have the chips necessary for you to have a controller over the motor. And then this is a donation from SEL. So our partner, they donate like microcomputers, but in our domain. So finally, this is the old version 2 years ago when we have the robots to coordinate in between charging stations. Yeah, so yeah, that's it. And should I ask you to, or I have the Q&A first? Questions and answers from me. Yes?
You said you did a computer science degree first in your undergrad. What led you to electrical engineering, specifically in power?
I see. I did my undergrad in electrical engineering.
Oh, okay.
I have 3 masters. So 1 master in machine learning from computer science, 1 master from statistics from pure math department, and the 3rd one is from electrical engineering. Yeah, the reason I did 3 is because I want to do a professor. Yeah, I want to be different. I want to have interdisciplinary analysis. Otherwise, you know, I'm following the other folks with the same class. How can I be better, right? So that's my position at that time. Yeah.
That's awesome.
Yeah, take more master degrees.
Please do.
Okay.
If you guys have questions about 4+1, please let me know.
Yeah. Yes.
Question, you were talking about the power senior technical elective, and you were saying that there was a 3 course that you would recommend for anybody that want to be doing with the power electrical. One was the generation and TV and utilization. So what are the numbers for those courses?
So for each one, we have 2 to 3. So 2 of them is they are fixed classes. The other one will be on rotation perspective. For example, I'm teaching a 598 class, so it's called machine learning for power systems. So that one will be part of the transmission and distribution portion. However, this class will be offered every other year or every other 2 years. So these classes are typically in a rotation scheme. However, I did discuss 6 classes. Are the students going to have the slide?
Yes.
Yes, okay. So when you look into... Okay, you will see there are 6 classes I'm talking about, then 2 for each division. Generation 2, transmission distribution 2, and finally the utilization 2. I can also quickly go back. Yeah, you can see I have 1, 2, 3, right? 1, right? 2, right? 2, 2. Yeah, 3, 2. Yeah. Yes.
On the topics of like energy storage, is there a specific class for it? Or discuss?
Okay. Yeah, there are special classes, but on a rotation scheme. You can send me an email. I can talk to faculty members who is in charge of that class. However, for the 6 classes you are looking into, we do not have a class dedicated to storage. However, a lot of classes are talking a lot of the storage device. For example, I'm teaching 479 right now. So I try to understand how the batteries is going to buffer the uncertainty in renewable generation like the solar panels and also the electrical machine consumptions like Tesla cars. So I dedicate maybe 1/3 of the class to talk about these issues. It's like storage device, stability, storage device, commercial reasons, storage device, application to the home level. So yeah, that will be my comment. Yeah. And also you can search online. There are storage classes from other divisions. For example, there are professors from the device division of our electrical engineering school. Yeah, they will basically talk about how you design the storage device from small component to the larger one. We are more from top to the lower part. They are like a bottom-up approach. Okay, and you can also do a senior design, right? Yeah, you can create it by yourself. Yeah. Any other question?
So is there only one nuclear plants class for us to take?
Yeah, there's one dedicated to that one. Again, for example, my class is on transmission distribution. I spend 2 weeks to talk about what are the energy sources, and then I compare all of them. For example, if you hate nuclear power, I will correct you. I said there are many benefits. So in the end of the day, you will have a table to see which resources for what reason and why we didn't choose it today. And maybe we will choose it in the future when the technology is mature. Yeah, I will say maybe half of the class will use nuclear power station as a starting point for the class. But that one is completely dedicated. Again, you can do a senior design with Dr. Hobart. Yeah, he has been in the field at least for 20 years. Yeah, so only about power, nuclear power station. Yes?
Are we allowed to build our own personal nuclear power plant for senior design?
Oh yeah, you can do that. Yeah, so there's no problem. We have so many connections.
Okay.
Yeah, so typically we have a tour every other year. All the students in the ASU hour program can go there. For example, I went there 2 years ago. So there were about 30 students, undergrad, master, and PhD, and then 3 or 4 faculty members. So we get inside to see their big monitor. We learn their safety manner, and then we go all the way to their generator to see all of those synchronous machines. Yeah, but I need to tell you, we don't get into the radiation zone if you want to go there. Okay. It's very dangerous. So there you cannot get inside.
If you're interested in nuclear, we do have a graduate level certificate. So if you're thinking of grad school or 4+1, that's a great add-on to do.
Yeah, so yeah, you can get a certificate, special recognition. Okay, I guess that's my portion. Yeah, do you want to talk a little bit?
Are you done?
Yeah. Do you want me to switch slides or it's only?
Yes, be my guest.
Yeah. So, this one, right?
That's it.
Yeah.
Yes, sir. Thank you.
Sure.
Appreciate it.
I will be your audience.
Oh, wonderful. Hello, everyone. Before I start, let me just get an idea of the audience. You're all seniors in electrical engineering? No. You're all juniors in electrical engineering? No. You're all math majors? You're all English majors. What are you people anyway?
Freshmen.
Freshmen.
Oh yeah. You're right.
Freshmen?
Sorry.
I thought this was the senior pathways course.
Well,
Start early? I know. Okay, good. Plant the seeds. So, do I need that?
Yeah.
Oh, you're recording? Yeah. Usually I can project pretty far after doing this for so many years. Sure. So, I'm Ronald Rodell, Professor Emeritus. Yes, that means, that's Latin for geezer, I think. I started here at ASU in the electrical engineering department in 1981. Most of you people weren't born yet, so that's as far as that. Oh, really? Well, good. That was when it was still Tempe Normal School, actually, not ASU. And I actually retired in 2011 and then came back to work in this program, the Professional Science Master's Program in Solar Energy Engineering and Commercialization. That's a mouthful. We haven't been able to figure out how to make it shorter. We'll just call it the PSM program. A Professional Science Master's is not the same as a Master of Science or a Master of Science in Engineering or a Master of Engineering. I'll explain in a second. And I'm, though, retiring for the second time, and hopefully the final time. I feel like the solar John Wick, you know? Everybody keeps asking me if I'm back. Yeah, I'm back. Terry Alford, who wanted to join me today, who's a professor in SEMTE, our companion school, School of Engineering of Matter, Transport, and Energy. So both the electrical engineering school and the SEMT school have the word energy as their last noun in their title. And it's because there's overlap. No one school has a complete monopoly on energy. In fact, I think the physics people would say they have something to do with energy too, and the chemistry people, and so on. But at any rate, which is the forward button? Does it matter?
Oh, yeah.
There we go. Okay. So the PSM program is a little bit different than any other master's program at ASU in that it's an overlap of 3 disciplines: engineering, business, and policy. And the reason we've chosen that sort of structure is coming up in a minute. It was started with a proposal that was funded from the National Science Foundation, and NSF was asking for new ideas in these PSM programs. And so Pat Phelan, who's a professor in mechanical engineering and also in the dean's office now, associate dean for graduate affairs, he and I were on a car trip together, and we decided we'd respond to this proposal. It had to be cross-disciplinary, it had to be cutting-edge technological field. There are about 300 PSM programs around the country, and nearly all of them, I'd say 90% are in the life sciences, biological sciences, and engineering. The remainder are there was one in nanosciences in the physics department for a while, but it's faded, sunsetted. Ours is the only one, as far as I can tell, in renewable energy. And so it's kind of unique. The proposal was submitted in 2010 and was awarded in 2011. Unhappily, just at the exact same time that it was awarded, I retired. And so I went, I can't believe it. I write all these proposals at NSF, they're never awarded. I finally retire, on your way out the door, here, we're awarding your proposal. And the terms of my retirement was that I couldn't teach at ASU for 3 years. Well, I could if I wanted to do it for free. And I love teaching, but I don't love it enough to do it for free. I'd rather panhandle, to be honest with you. So, but in 3 years' time, they said you can come back, and I did, May 16, 2014. And I came back just to teach one course, and then I ended up teaching 2 courses, and then I ended up teaching 3 courses, and then I ended up becoming the damn director of the program. So actually, emeritus is Latin for mission creep. It just continues to grow. So I've had enough. I have to hand it off to somebody else. I'm getting too old to continue this. It's a brilliant program, and I'm very happy that I returned to the university to continue and to help to establish this program. The first director was Dr. Phelan. The second one was Harvey Bryan, who's a professor of architecture, and he and his students were responsible for the solarization of ASU. If you look at any building, you see PV on top of it. Dr. Bryan had something to do with it. They did a study of all the rooftops, what they could support in terms of solar, and they figured out ways of financing it that cost the university zero money out of pocket. And so then I was the third director, and now Professor Alford will be taking over. Now, it's a advanced interdisciplinary education program. We accept students in almost any field in science, technology, engineering, mathematics, architecture, business, policy. I have several students in the class I'm teaching this term that are from power engineering. There are seniors in power engineering, electrical engineering. There are some who are from physics. There are some in chemical engineering. There are one in architecture and 2 in business. So it's designed, we think, to enable solar energy, produce solar energy, people ready for solar energy careers in any portion of the industry, government, and nonprofit sector. And it's systems oriented, so it's not intensely math heavy, and it's not a physical science program. We don't talk about electrons and holes in semiconductors more than once. We don't talk about sinusoidal power and reactive power and voltvars and all that more than once. We spend an awful lot of time talking about net present value, business calculations. We're going to build this system, what's it going to be worth in 20 years kind of calculation. So It's, in addition to having a bunch of technical and non-technical courses spanning a number of schools, the students get to do an awful lot of interaction with policymakers and the local solar industry, and they complete an applied research project in place of a master's thesis. So it's a project that's of relevance to somebody in the local industry or government, and usually, it doesn't have to be local, it could be somebody in Massachusetts or somebody in Africa or something like that, because we do have those kinds of projects. The idea is you work closely with an academic and an industrial advisor to define and work on something that's of immediate and current interest. It's kind of like President Crow's mission statement of making the university a force in the community and working on projects that has an orientation for interaction and growth. It's a 12-month program, not a 9-month program. It's a 1-year program, but not one academic year, one calendar year. And so here's like the difference between a PSM program and a Master of Science, which many of you might pursue. Dr. Weng took 3 masters, for Pete's sake, so you should have taken one of these while you were at it.
Right.
Can complete the master's kind of flavors, Master of Fine Arts, maybe that's next for you? Or
Yeah, I should
sure, why not? Both 30 credit hours long, usually a master's thesis for the science, but a 6 credit hour applied project. Master's of Science is 2 years, this is 1 year, and you also can combine it with the 4+1 program to make it like a 0.75 year program with double counting that you get to do with the senior year. It's cross-disciplinary, enterprise-oriented, and it has involved a number of other additional amenities, a trip to Washington, D.C. to meet policymakers, legislators, lobbyists, and so on, to carry out. We're not doing it this year because we weren't able to at the last minute, but usually on spring break we send the students off to some place to do a rooftop installation, usually in some economically deprived community. So it's a bit of a charitable work, learning something about environmental and justice and energy justice, but also to get some hands-on training on bending conduit and putting PV on a rooftop and so on. And the students come back thrilled by doing it, and the people who get a free PV system on the roof are delighted too. We send the students to all the meetings, to AHJ, authorities having jurisdiction, so to the Corporation Commission, to legislative groups, to a variety of other places, to city councils to talk about the importance of renewable energy or electric vehicle implementation or so on. I spent the last 2 days, as a matter of fact, at the Corporation Commission, because they've been holding hearings on turning Arizona into a state that would have retail electricity competition. That would be a real game changer. No, you don't get the electricity from SRP because you live in SRP territory, or APS because you live in APS territory. You look through a menu of who you'd like to buy electricity from. Sort of like your cell phone. You don't have to just get Verizon, Anyways, I sometimes, in the classes for homework, the students have to attend a Corporation Commission hearing, or they have to respond to a notice of inquiry from the Corporation Commission, and they have to file the papers and bring them down to the commission headquarters and file them in the docket. And they go, geez, legal stuff too. And yes, it's all part of the business. So here's our model. Engineering is done in the business world, and business is carried out in the policy world. And you might not learn that when you're in college. In university, we tend to have the ivory tower syndrome. We think of ourselves as isolated, independent of everything else, especially that vile stuff like making money. But if you leave here and get a job at SRP or some smaller company, if they don't make money, they're not going to keep you on. There is no business in this world that can be unprofitable. I don't mean non-profit. I mean unprofitable and stay in business for very long, unless Michael Bloomberg's paying for it or something and just throw hundreds of millions at it forever. And businesses get to proceed forward or get set back depending upon the policy climate they're working in. It's especially true in the energy business where there are legislatures and there are corporation public utility commissions that make decisions about rates you can charge, about implement how much renewable must be in your portfolio, et cetera, et cetera. That's established by policies. So you have to know what those are. And guess what? In all 50 states, they're different. And so in this program, you have to become an expert on 50 states worth of policies, business climates. Oh, then you have to think about this globally too. Many students in graduate school are international students, and they come from China, they come from Africa, they come from Europe, they come from India, they come from Australia, and they all have different policies, and you have to learn about them as well. Because you might not stay here in America, you might move elsewhere. Remember, the sun shines on all of us. We have a major emphasis in this program on reading, writing, and presentation. So you might start thinking you're in an English class when you take one of my classes. What? Another report to write? What? You took off points for grammar on my homework set? Yeah. You have to speak the King's English properly. Well, American English properly. The basic degree map for the fall, spring, and summer is in the fall, the required course is Solar Energy and Engineering Commercialization 1. In the spring, there's a Solar Energy Policy course. In the summer, Science Outside the Lab. That's the course on going to Washington, D.C. You actually get academic credit for that, but you have to earn that academic credit by writing some papers before and after the Washington trip. You write the papers being naive about what they do in Washington, then you rewrite the papers when you get back and you go, I had no idea this is the way things are done there. Okay, let me revamp everything I've said. The other technical electives and non-technical electives can be chosen from an immense array. There can be power courses like Dr. Weng showed. It can be science classes, physics classes, additional classes from Poly. By the way, the Polytechnic campus has a fair amount of work done on alternative and renewable energies too. Nathan Johnson has a course on microgrids alone. It's an exceptionally good course, and he's a terrific instructor. And Dr. Manny Govindasamy Talmamani, my hero, who runs the photovoltaic test labs out there, teaches a course on reliability and standards for solar modules. Dr. Srini teaches courses in operations and maintenance. All these things are part of the same picture. And to answer your question about batteries, Candice Chan in chemical engineering teaches a fantastic course on electrochemistry and with an emphasis on batteries. So you might look into that. I don't remember the number. It's CHE or MSE something. Well, Candice Chan, C-H-A-N. Look her up, find out what she teaches. I suggest to a lot of students they take that class. In the past, solar energy used to be a standalone idea. You make solar cells, you make solar modules, and then, geez, somebody will put them on a rooftop someplace. But the thing has changed so much. The whole business has reoriented itself and expanded so much in the last 10 years that in the very near future, solar plus storage will become one word. There will not be a solar system without a solar energy system. Okay, solar system's an astronomical thing, that's different. Without batteries too, it'd be like going to a car dealership and buying a car and saying, do wheels come with that? Yes, wheels come with this. And because that's going to be one of the key factors in the continuing expansion of solar energy. So a lot of the applied projects that students are doing now are related to new storage ideas and not just battery ideas. Larger scale storage ideas. I think I might have a chance to present a couple of those. This is students working on the solar spring break. It looks like a ground-mounted system they're working on. This is recommended, but it's not required. This interdisciplinary applied learning lab was a course, I don't know if we're going to offer it anymore, that was taught in conjunction with people from the Carey School. So business students and engineering students learning to talk to each other. kind of worked, but not as well as we'd hoped. There's Washington, of course, and that's part of the DC trip. So there are so many options. Solar engineering and commercialization 1 is a course on the whole PV enterprise with an emphasis on the residential and commercial industrial, the smaller scale PV systems, rooftop systems. So everything from design and installation, permitting, commissioning, and so on, to financing costs, business paybacks, to policies that help the rooftop solar move forward, et cetera, et cetera. The second solar energy and commercialization, which I'm teaching right now, is utility scale, and how to build and find land for or water bodies for the new floating PV. Maybe you've heard of this, really interesting stuff. If you have no land but you have a lake, gee, that's a good place to float PV modules on rafts. And you can make them quite large. Very popular in the Pacific Rim countries where land issues are restrictive. Here in the Great Southwest, which includes California, Nevada, Colorado, Wyoming, New Mexico, and of course Arizona, there are large swaths of land owned and operated by the Bureau of Land Management, or BLM for short. And they've been going through a process for the last 8 years or so on defining regions that would be very suitable for large solar farms. The farms are the size of 100 megawatts to 1 gigawatt in size. So 1 gigawatt is a very large solar farm. The Palo Verde nuclear power plant, just 60 miles to the west of us, is 4 gigawatts, largest nuclear plant on the planet. 4 of these solar plants would have the same maximum power output as 1 nuclear power plant. What's driving some of the large-scale solar farms now is 2 things. 1, Salt River Project has announced it's going to build another gigawatt of solar farms in 5 200 megawatt increments starting this year and then going forward. They'll be looking for land, whether they're going to do it on properties they already own or can lease, or the solar energy zones remains to be determined. The solar energy zones are regions that the BLM has identified as meeting all the requirements that make it good. No proximity transmission lines with capacity, essential. Properties that don't require much grading, properties that have no endangered species issues, properties that don't have archaeological artifacts to worry about. So they're basically lands that are just crying out for the sun god Apollo to bring his sunshine down onto the modules there. There's one, I went to a BLM hearing last week in Quartzsite, Arizona, beautiful little Quartzsite. Beautiful is the wrong adjective. Ugly little town of Quartzsite. It's 20 miles from the California border along I-10. A company called 174 Power wants to build a 1 gigawatt solar farm along I-10, and they can connect to the 10 West link, which would be power sent to California, largely. Although, there is some return. Anyways, that's what I'm teaching right now. And it's a fascinating thing. I came to ASU as a solar cell engineer, worked on that for a few years. The funding for that dried up, stayed in other semiconductor stuff. But now I've realized that just building solar cells isn't enough to make the solar energy enterprise move forward. APS, as I said, SRP has announced another gigawatt. APS has just announced that it's going to, by 2050, be carbon neutral. No fossil fuels in its system anywhere, unless it's a natural gas plant from which they believe they can carry out carbon capture and sequestration. There's an interesting research idea. They view nuclear power as clean, not necessarily renewable, of course, but clean in that it doesn't emit CO2 during its operation. But they're also going to make their renewable portfolio 45% by 2030. Now, this is the same utility that really fought hard against rooftop solar and other solar for the longest time, because all integrated monopoly utilities make their money by getting a percentage, a return on investment on their rate base, all the physical equipment and plant that they own. What they disliked about rooftop solar is they didn't own it any longer. Somebody else owned it. So there was load defection, and it was bothering them at their core in terms of the profits they could make and how they would get a return on investment. They've had to change their heart. A new president who says, well, got to move away from fossil fuels. It's a disaster for the environment, and we can do it. We can do it with renewables, solar, wind, and nuclear. So this is a great time to be a renewable engineer. You will have also a lifetime career too. Oh, yeah. Don't want to be a coal miner. That's a very short, limited job. You'll be able to do that for another year or two, and then it's all going to be gone. Do you have a question, or are you just stretching?
Yeah, I have a question.
Sure.
For the houses that are in like APS territory,
Yeah.
they have solar generation. Does that count towards APS's 45%?
No. Well, maybe. They can't count it as their own because they don't own it. But they can count it in the overall mix for their integrated resource plan. So they can say, within our service territory, we own so much solar, and we have customers who are grid connected to us who also have solar. So yes, we will call that part of the meeting the renewable portfolio standard, and part of the 45% by 2050. Yeah, so there's two ways of counting it. And both are legitimate. You just have to understand which one's which. We have some super professors in this program, and they're from a variety of disciplines. Dr. Pasqualetti from geography, who's got an international recognition for water and energy. Dr. Bryan, I mentioned, architecture. Dr. Bennett in the policy, who's not just got a national recognition, he's got this great TV show on PBS talking about policies and TV. Chris Mays is she's in the law school, but now she's, I think, also in that policy school. And she's a former ACC, Arizona Corporation Commission commissioner, former chair. She was the one who wrote the Renewable Portfolio Standard that's in place right now for Arizona. Terrific addition. And of course, Dr. Manny, who I think has an intergalactic reputation. It goes beyond the edges of our world. All the modules that were in the movie The Martian, I'm sure he tested personally before sending them up there. Okay, that's a joke. I think I'm running out of time, so I'd just like to move forward and say that here's what the recent applied projects have looked like. This is not all of them. Too many to put on one slide. But some of them they all have a system flair. None of them are thinking of the next semiconductor to replace silicon as the material for solar cells. With all due apologies to my good friends in Quest, the quantum electronics and sustainable solutions, I forget what their Quest stands for, but they're trying to find new ways of making cheaper solar cells, and I say good luck. Silicon, Mother Earth is made of silicon. It's one large silicon ball designed to be turned into one large solar cell. Really, after oxygen and nitrogen, silicon's the third element. And it's benign. You could sprinkle it on your mashed potatoes and eat it. It wouldn't hurt you. It's not toxic. It reaches out to Apollo and says, shine on me. Anyways, so we don't work on solar cells. We work on things related to the whole solar enterprise. So monetizing the value of shade in solar structures. Everyone knows that shade's a good idea, yeah? What's it worth in terms of dollars and cents? Well, there's a way of calculating that if you apply some business principles to it. Gravitational energy storage, I think, will be a big deal in the future. There's several versions of it. It all boils down to MGH, folks. Take some heavy mass and move it from a lower to a higher level, then let it run downhill through a generator. Or it could be a weight on a very large electric vehicle or train track that runs down the hill and uses regenerative braking to produce power, fed back to the grid. So instead of just 4-hour batteries, which is what most battery designs are for, and they're designed to help do peak shaving and help the help the grid stability when the demand is enormous at the end of the day. This can be much longer term stuff. One of my students right now is working on, get this, it's a great idea, I think. Well, it's my idea, so I think it's a great idea, but I've convinced her it's a great idea too. We have a lot of abandoned mine pits in Arizona. They're horrible eyesores. They're toxic, they're dangerous, and they're abandoned. And they just sit there waiting for, I don't know what, meteors to fall in and fill them in? Who knows? Hey, they got tracks that run all the way down to the bottom. Let's put railroad tracks in there. Some even have railroad tracks. Put cars on them filled with very heavy weights, roll them up the hill by using solar-powered generators, the electric generators, motors that can bring them up, then run down the hill, and so we can turn that eyesore into a productive spectator sport. Let's see how fast these things can roll downhill. She's going to do an inventory in all the pits and figure out what kind of process we made. Floating solar farms. Supercapacitors. I was an electrical engineer who said, I think supercapacitors should make a revision here, a return. This one is really cool, and I'll end with this. The Athena Combs worked on a design that could be entered into the LAGI competition, Land Arts Generator Initiative. It's this organization that's worldwide. Once a year they have a competition where they accept ideas for some solar project in some particular location. The last one was in Melbourne, Australia. And she had to design some sort of PV powered system that met a particular lighting and electricity need at a museum. So, and all of the designs have to have some sort of architectural or crazy flair. Google L-A-G-I, LAGI, and you can see what some of the designs look like. So her applied project was to enter that competition. It's kind of neat. So if you have an artistic flair. Now, I'm not trying to, here we are in Washington. That's me stepping out of meetings with Dr. Trump to talk about science. Here's where our students go when they graduate. First Solar hires a lot, McCarthy, Amoresco, those are the developers and builders. Rhineland-Tooth, a couple have gone to the Corporation Commission. They're my insurgents, my moles, to tell me what's going on there. And we don't have the fall 2019 data yet gathered, but 94% of the graduates from this program found work within 6 months. Starting salary average 67. The 73% got a job in the solar industry. Some said, I liked it, but I'd rather work in something else. Certainly it's not indentured servitude. So there you go. The Executive Solar Energy Graduate Program. So keep it in mind. Now, we can work in cooperation with the power people, with the poly people, with the chemical engineering people. Everybody is welcome. We share courses in the the utility scale course I was talking about. Half of the students are not in the PSM program, and they're all power engineering graduate students who want to learn more about a slightly different outlook on the utility scale energy generation, transmission, and distribution than the traditional power engineering approach. Not wrong, just more complementary, I would say. So that ends my discussion presentation. If you have any questions, please, I have some cards here if anybody would like one. You can email me, and then I'll forward it to Dr. Alford, who will then be answering all the questions in the future. Okay. Thank you for your kind consideration.